So what's the relationship between dl, L, and d theta? dl is equal to, what were you saying? Tangent? She says tangent. Do you agree? What is that? L times the tangent of d theta gives you dl. Is that what you're saying? Right? So here's L, and there's dl, and this is a little angle d theta, and that's a right angle. So is dl, so let's see, the tangent of d theta should be equal to dl over L. Is that what you're saying? Is that right? Can I simplify?
Yeah.
How?
Well, let's simplify.
Yeah, I want to simplify this.
That's more or less equal to.
That's pretty much d theta. In the limit, as d theta goes to 0, the angle and the tangent and the sine all go to the same thing. So this is going to be d theta is equal to dl over L. Are you okay with that small modification?
Yeah.
Okay? Whew. Dodged a bullet. All right, so in the limit, as dl goes to 0, these are two sides of an isosceles triangle that's basically got 0 for this angle, so both of those are about right angles. So dl is L times d theta. I think that should be consistent. Yeah, that makes sense. So what's the precession rate? So I'm going to use capital omega, not little omega, because little omega already represents the spin angular velocity of the wheel about its axle. So I need another rotational velocity, and I'm going with capital omega, which looks a little bit like a horseshoe, or ohms, depending on if you're a meditator. Yeah, thanks. So capital omega is the time rate of change of this angle that describes the direction that L points in. And does this follow tau over L? Does that work? Seems like this is the same as the magnitude of that. So this would be tau dt. So put the dt down here, put the L. Yeah, that works. So let's stare at this for a moment. This says the rate at which the bicycle wheel will precess is the net torque divided by the spin angular momentum.